looks like number 2 here. So, and the problem is, so I think, and I hope you would agree with me, that since it's the same ramp as before, as in problem number 1, then I think it will have the same acceleration down the ramp of 0.75 meters per second squared. So it's the same ramp. And we are pushing it up the ramp with an initial speed of 2 meters per second. And we know that the ramp is 2 meters long, but we don't know if the marble makes it all the way to the top or not. So it might be confusing which of these bits of material we would want to use. Now, so when I recognize that I'm dealing with a kinematics problem, and it's really easy to know when you're dealing with a kinematics problem. It's going to mention things like displacement, acceleration, and velocity. That's a clue to you that you're dealing with a kinematics problem. The first thing I'm going to do is I'm going to list out all of the kinematics variables. And I'm going to put a bar over the top of the ones that I know are vectors to remind me to take into account whether they are positive or negative. Now, as an aside, I will know that there are relationships at play as well here. Now, I didn't write these in a random order. If you look carefully, I wrote them in a very specific pattern. Delta X is missing from this one. V naught is missing from this one. V is missing from this one. Acceleration is missing from this one, and time is missing from this one. Do you guys see that? I wrote them in that order on purpose. It's a rubric. I'd make your note card the same way. Now, I know you're trying to write them down. So I think this part's not so terrible. When you're trying to acquire information that's been given in the problem, anything in meters is probably going to be here. Anything in meters per second is probably one of these two. Anything in meters per second squared is probably this one. Anything in seconds is probably that one. So don't put stuff in the wrong spot. I mean, don't use stuff that's not appropriate to use, of course, but you shouldn't put things like a displacement where a velocity goes. That's just silly. You're going to be given a problem with the units. It's pretty clear that you're going to have to sort those out. The problem says that the ball is pushed up the ramp at 2 meters per second. That's the starting velocity. And we are told that the marble is experiencing an acceleration of 0.75 meters per second squared. Now, this is where it gets a little bit confusing. We don't know if it makes it all the way to the top or not. So we have to decide what we're going to do now. Now, if it doesn't make it up to the top, and I assume it does, I will probably get some weird stuff go on with my math. So I'm afraid of just assuming it makes it there. What I'm going to do instead is I'm going to try and figure out, well, where does it stop? If it stops at a displacement that's greater than 2 meters, then I know it makes it up to the top. If it stops before 2 meters, I know it didn't. So I think that's the first thing I'm going to do. I'm going to find out where it is when it stops. Does that make sense? And again, if it's greater than 2 meters, well, then I'll redo the problem. If it's less, then I've answered the question. All good to go? Now, before I go on, anything with a bar in it has to have its direction added. You need to make a decision about direction. So I'm going to choose to make up the ramp positive. And any of these numbers that are vectors, I'm going to make positive if they're going up the ramp and negative if they're going down the ramp. And I am super explicit about it because I don't want to forget to do that. That's going to be a consummate problem all year long because every one of our units has vectors involved. So be deliberate. There's always going to be a step that says, check the direction of your vectors. So step 1, write out your motion variables. Step 2, glean what you can from the problem. Step 3, decide on a direction for positive. Now, if you're careful and you organize yourself, the choice of what to do next is right in front of you. You'll notice we are trying to figure out delta x. We want a function that has these 4 things in it. Whatever motion variable has been left out, if you organize yourself the way I did, that function will have the 4 things in it that you need for this particular question. That's why I organized it this way. So for those of you who don't want to think very hard, you don't have to think very hard. There's always going to be an equation that has 4 motion variables in it, and you have to be given at least 3 of them to make the problem work. So this is what we have. So I will use that bottom one to work out my answer. And that's going to be 2a delta x equals v squared minus v naught squared. Now you're noticing I'm not writing the vector bars in the formulas as I work. They just become distracting. It's okay. As long as we already know that we've taken them into account, I don't have to keep reminding myself that they're vectors. So 2 times negative 0.75 delta x equals 0 minus 2 squared. We good? Any question about that? So negative 4 here, negative 1.5 delta x here. I know this, 4 divided by negative 1.5 is going to be greater than 2. So it makes it to the top. But I don't have to go any further. Do you follow what I just said? So I don't really care what the answer is. If it's bigger than 2, then it leaves the ramp. So I have an answer, but it's not the answer of my question. The question wants me to find out how fast it's going when it makes it to the top of the ramp. I now know it makes it to the top of the ramp. I have a different problem to do. So I'm going to reconsider my variables here. I'm going to say that I'm not looking for where it stopped. I'm interested in how fast it's going when it makes it to the top of the ramp. Now, I'll point out the same relationship is going to solve this problem as the last problem. So I'll just do 2 times negative 0.75 times 2 equals v squared minus 2 squared. Looks like 2 times negative 0.75, that's negative 1.5 times 2 is negative 3 equals v squared minus 4. So v squared equals positive 1. So v equals 1 meter per second. I made a mistake. I'll wait for you guys to write some things down, and then I'll talk to you about my mistake. So it's not a math mistake. I left something out intentionally. So make sure you're caught up. Everybody see the arithmetic? Any problem with the arithmetic? I'm not doing a lot of algebra here for you. I'm not going to show you every step. So if you don't see something or you think something is wrong or you don't understand something and you decide not to ask about it, that's really going to have to be on you, okay? Can I talk about what I left out? We're all okay with the answer being 1. V squared equals 1. When I take the square root of both sides, I am required to consider both roots. There were 2 possible answers here, positive 1 meter per second and negative 1 meter per second. You should always consider both roots whenever you take the square root, always. So I had to decide which one of those answers did I think was the right one. So don't just jump to the fact that it's 1. It could be positive 1 or negative 1 because that tells you your direction. This one, positive 1 was the right answer because it's going up the ramp still when it leaves. But what this also tells me is probably if the ball could continue up the ramp, when it makes it back here, it'll probably be traveling the same speed, but now in the negative direction. It lets me know something about maybe a different problem or a different type of question. So don't always assume. And we're trying to figure out when the car is back at its original position. So 0 equals 1/2 times 2t squared minus 4t. We can solve this for t, but there are two answers. And I think you guys would generally do this and only find one. But you have to remember how math works, especially in this class. So when I multiply the half, I get t squared minus 4t. Now, some of you might feel like we can just add 4t to both sides and then divide by t, but we can't. In order to get the correct answer, we need to find both factors and set each factor to 0. So I'm going to factor out a t. And remember that in a quadratic, there are often two answers. So this is a quadratic. I will set each factor equal to 0. And this produces two answers. T equals 0 seconds and t equals 4 seconds. Now, it's important to understand that we asked the mathematics to tell us when the car was at the starting position. And it was at the starting position twice, both at the start of the interval and then 4 seconds later. It's a good idea to always find both of your roots of a quadratic. It helps validate your answer. It helps ensure that you're getting the right answer. Because if you did this and got, say, two positive numbers, you might be confused as to where that came from. So it's often best, if you have a quadratic, to find the two roots. So also, when you divide out a t here, you're dividing by 0, and that's not allowed in math, which is why you have to do it this way. So I think there's two questions being asked here. So I'm going to go through and talk about what happens to the car first, and then I'll go back through and talk about what happens to the occupant next. Is that okay? For the car goes from 20 meters per second to 0 meters per second in the distance of 1 meter. The occupant, using a seatbelt, still goes from 20 meters per second, because they were part of the car, to 0 meters per second, hopefully. But they're going to take 2 meters to do so, right? Crumple zone plus your movement through the airbag. What was the acceleration experienced and the time for each? So now that we've set it up, although it is two separate questions, it's the same question largely, right? We're just going to be doing the same procedure twice. Let's work on this one first, since it represents the car. These are our vector values. Everything's in the positive direction. So I think our acceleration is going to be negative, but we're going to make everything in the positive direction. So I'm going to choose a relationship that has everything in it except for time first. That will be 2a delta x equals v squared minus v naught squared. That'll solve the first question. What's the acceleration experienced by the car? So 2a plus 1 equals 0 squared minus 20 squared. 20 squared is 400. 2 times 1 is 2, so a equals negative 400 divided by 2, or negative 200 meters per second squared. Okay? What's the acceleration due to gravity again? 10 meters per second squared, which means this is 20 times g. Or you could say that the car would have to experience 20 g's of acceleration. Have you ever heard that phrase before? Experiencing an acceleration? This is probably not particularly survivable. 20 g's of acceleration is a lot. Humans have endured way more than this, but this is a hard acceleration. You're probably not coming out of this acceleration without injury. That's why we invented things like seatbelts and airbags, to try and change this number. Now, we haven't finished the question because we're also supposed to figure out how long it takes to come to rest. So we should do that too. I'm gonna use, again, I try not to reuse anything I solve for if I can avoid it. So I'm not gonna use the acceleration, I'm gonna use the given information. And that would bring me to this relationship. I mean, you're welcome to use something you solved for in the past, but I encourage you to always use the given information when you can. And delta x is 1/2, 20 plus 0, t. So half of 20 is 10, 1 divided by 10 is a tenth, so 0.1 seconds equals t. All good? At the rate that some of you are writing this down, it's clear some of you didn't do this one. We're going to repeat the whole problem, but we're going to change that to 2, right? The people get 2 meters to slow down in. So let's do it. So I'll put a 2 in here. That's still going to be 400 on the other side. My acceleration is now negative 100 meters per second squared, or 10 Gs. That's way more survivable. Way more survivable. Probably still going to be feeling it in the morning, but you're probably walking away from this. You can routinely get, we have rides at the theme parks that get us up to around 7 Gs. So a little violent car accident, yeah, but you were going 45 miles an hour to 0. That's a pretty huge acceleration. 20 meters per second is about 45 miles an hour. All right, 2 equals 1/2 times 20 plus 0 times t. So this gives us twice the amount of time at 0.2 of a second. All right, that was question number 10. So this is number 6, a free fall question. You guys did a lab on free fall, and we're supposed to determine what the acceleration due to gravity is for something that's in free fall. I told you what the accepted value is, didn't I? What was the accepted value? 9.8 meters per second squared. For problems like these, though, it's acceptable for you to use 10 meters per second squared. It makes the math easier. And that's all I use here in class. You can use that on the test as well. The test will actually state it, so, but for us, you can. All right. So I like to draw a quick picture of it, and I have largely just kind of thrown this stuff at you, meaning I gave you everything you need to solve these problems, but what I'm going to do with this first one is give you a series of steps to solve it. This is helpful for those of you who have a difficult time organizing yourself. So if you're that person and you've yet to learn how to learn on your own, I mean, learn how to organize your thoughts and put them in order, I will give you a method that will solve these problems without you having to do too much thinking. Okay? So this problem begins with the rock being dropped off the side of the bridge, and it falls, and we hear a splash 2 seconds later. And we're asked how tall the bridge is. Is that basically it? Now, I can tell that this problem is a kinematics problem for a number of reasons. One, it's free fall. We're using the acceleration of gravity. That's usually a big indicator that it's going to be a kinematics problem. Also, we're given other kinematics information, like an initial velocity of 0, time of 2 seconds. These all sound like properties that are associated with our motion problems. We know that in motion problems, we have 5 pieces of information that we've been discussing over the last couple of weeks and how they're related. And we know that 4 of these are vectors, correct? So on the AP exam, they're not going to say, this is your kinematics problem. You're going to have to know when to use kinematics. There's 3 hints here that this is kinematics. So I gave you what those 3 hints are, but there's one big one here too. G is a constant near the surface of the Earth. So when you have things that are having a constant acceleration, that's probably kinematics. Now, we have shown over the last couple of days that there's a group of relationships associated with kinematics. There's actually 5. That's one. This is another. And I've written them all out at various times. Here's a third. And the last. Now, you've had these, but now I've organized them in a different way. And it's organized like this on purpose. To the left is the motion variable. To the right is the equation that doesn't have that particular motion variable in it. So this one doesn't have delta x in it. This one doesn't have initial velocity in it. This one doesn't have final velocity in it. This one doesn't have acceleration in it. And this one doesn't have time in it. In fact, I made a special video just for you guys where I talk about this. Now, each one of these has units associated with them. Second squared, meters per second, and meters. It should not be hard when reading a problem to discern what's been given to you, since they're going to come with the units. So, except for velocity, it should be pretty easy to sort them. Agreed? Now, on your very first test, I don't let you have the equation sheet from the AP. The reason is because the equation sheet from AP has hundreds of equations on it. It's very distracting. I will, however, place these on the exam, or on your first test. But for tomorrow, if you had a note card with these 5 things on it, I would let you use it. Does everybody understand? So you have until tomorrow to have a note card with these 5 things on it. If you don't get to use one, and you don't get to use your friends. How do you have a question?
I was just going to ask if a sticky note works too.
Okay. But I don't want to go over all the possible permutations of what could have these things on it. It should be small enough where it's just for you. Okay? I might be nice enough to put them on the board, but I often forget. All right? Here we go. Let's talk about this question in particular and how we might use this to solve our problem. You drop a rock off a tall bridge and you hear it splash after 2 seconds. How tall is the bridge? Well, drop means the initial velocity is 0. And as this is a free fall problem, the acceleration is 10 meters per second squared. Now, you have to be given 3 pieces of information or else these problems can't be solved. So the information is going to be there. So as you look at the information presented, look for the 3 things, because every one of the equations has 4 things in it. So you need 3. So it's buried in there somewhere. After you've done this, though, remember that each one of those top 4 is a vector quantity. You'll have to decide what direction you're going to call positive. So I have a choice to make up positive or down positive. What would you guys like? You want up to be positive. Okay? That means my acceleration has to be made negative. We'd like to know how tall the bridge is. I think what we really want is the displacement of the rock. That would tell us how tall the bridge is, because the rock had to go from the top of the bridge to the bottom. Now, if you've organized yourself the way I've organized myself, when you look at your equations, you'll notice that you were given 3 pieces. You're looking for a 4th, but one of them wasn't mentioned. Do you see that? The one that wasn't mentioned, you weren't given, and you don't need to find it. If you organize yourself, that suggests this relationship will have the 4 other things in it. And that's why you should organize yourself like this. You don't have to do very much thinking. So I'm going to choose that relationship because I know that all 4 things will be represented. So delta x equals 1/2 at squared plus v naught times t. So 1/2 times -10 times 2 squared plus 0 times 2. 2 squared is 4, half of 4 is 2, 2 times 10 is -20 meters. Now, the answer is 20 meters, not -20. The rock fell downwards 20 meters, but how tall is the bridge? It's 20 meters. All right? That's the first part of question number 6. Are there any questions about what I've done? It took extra long to solve that on purpose for all of you who didn't know where to begin. You no longer can say that. From this point forward, you have a where to begin. Write out your motion variables, draw yourself a picture, choose a direction to call positive, fill in the information that was given. Look to see if you have 3 pieces. If you do, find a relationship that has those 3 plus what you are looking for and solve it. That's just arithmetic. If you instead throw the rock upwards at 10 meters per second, how long until you hear the splash? It sounds like we need to know how tall the bridge is to solve this problem. Would you guys agree? So we now know the bridge is 20 meters tall. All right. So with the bridge being 20 meters tall and the rock being thrown upwards at 10 meters per second, I think the rock is going to make a path that goes up and then back down, and then it's going to hit the water. Would you guys agree with that? Any question about that idea? The rock's going to have an initial velocity of 10 meters per second while still making a displacement of -20 meters. Right? It's still landing 20 meters below where it started. The acceleration of the rock is going to be still g, so -10 meters per second squared. We'd like to know how long the rock is in the air. Any questions about the choices I made there? Because this one has a bit of a hiccup in it. And we'll see if you guys are capable. I need a relationship that can be used to solve for the time. I'm going to not use anything that has to do with the final velocity, and I'm going to use the same relationship as before. So, delta x equals 1/2 at squared plus v naught times t. So I have -20 equals 1/2 times -10 t squared plus 10 t. Any question about where any of that information came from? Alrighty. I want to solve this for t, so I'm going to have to do some arithmetic to do so. But I notice that this has a t squared in it and a t, so I'm probably going to have to be dealing with a quadratic. That doesn't scare me. Does it scare you? If it does, you're going to have to get over it and figure out how to do it. We'll get there and see what tools we have available. So I was trained to get everything onto one side when you have a quadratic, so that's what I'm going to do. So I'll move the 20 over. I'm also going to use that 1/2 times 10. Everything is got a factor of 5 in it, so I'm going to pull out the factor of 5. Actually, I'm going to pull out a factor of -5, if you don't mind. Okay? Now, I'm going to look to see if this is factorable. I can consider that 4 has 2 sets of factors, right? 2 and 2 and 4 and 1. Is there any combination of those two factors that could give me a middle value of 2? You guys remember how this works, right? I just don't think there is. The best 4 and 1 could give me was 3, and 2 and 2 is going to give me 0 or 4. So I don't see that I'm going to be able to factor this. So I have 2 other choices. I could graph it. You'll have access to a graphing calculator. If you know how to get the roots of an equation from a graphing calculator, by all means do so. It's not hard to do. You also, on the actual AP exam, you'll have access to Desmos. How many of you have used Desmos before? Okay, this will need to be 100% of you because there's absolutely no reason not to use it. But if you don't have that tool, then you're going to have to do it the way you were taught in 7th grade. Negative b plus or minus the square root of b squared minus 4ac over 2a. You have it memorized. You are required to memorize it. And I don't accept, no, I don't remember for an answer. So let's go. Since that seems to be the one thing most of you have in common is you passed Algebra 1, because I have checked your grades. So negative b plus or minus the square root of b squared minus 4ac divided by 2a. All right? This is what b will equal. There's also completing the square, but I don't remember how to do completing the square. Do you guys? Once I learned this, I stopped doing completing the square. All right, so this is 2 plus or minus the square root of 2 squared is 4 minus 4 times 4 is 16, but it's going to be made positive, all divided by 2. So 2 plus or minus the root of 20 over 2. 20 has a 4 in it, so I could write this as 2 plus or minus 2 root 5 over 2, or 1 plus or minus root 5. Just stuff you guys all should know how to do. It's pretty straightforward. I'm noticing right away, though, root of 5 is greater than 1. So there's going to be both a positive root and a negative root. Negative time generally gets thrown out. So I probably only care about the positive root here. So you guys can figure out what 1 plus the root of 5 is, because that's your answer. So this is number, you said this number, which one? 9. So I see another question after this, but we'll hit this question mark first, and then we'll hit the next question mark afterwards. Is that okay? So I do like to draw quick little pictures, but I'm not going to draw the whole roller coaster car. But it says that the roller coaster car starts from rest and accelerates over a distance of 12 meters to a speed of 30 meters per second. So its initial velocity is 0, final velocity 30 meters per second. What is the acceleration experienced by the riders? Okay. I will start by writing out my motion equation variables. I'll try to ascertain what's been given. Looks like it moves 12 meters, starts from rest, and gets up to 30 meters per second. I'm going to make to the right positive, which makes all of these positive. What is the acceleration experienced by the riders? That's the same as the acceleration experienced by the roller coaster cars. I've identified 3 pieces of information. I'm looking for a 4th. I'm going to choose a relationship that has everything in it except for time. That'll be 2a delta x equals v squared minus v naught squared. Any question about where any of that came from? Okay. 2 times a times 12 equals 30 squared minus 0 squared. 30 squared is 900. 2 times 12 is 24. So a equals 900 divided by 24. I don't know what that is. You can probably figure it out. If you care about the answer. I'm indifferent. But I think we have to compare it to something else in a minute. So we should probably get there. Yeah? What is it?
37.5.
Thank you. That would be meters per second squared. All right. When you shoot an arrow from a bow, it travels 0.75 meters, the length of the arrow, while accelerating from rest to 80 meters per second. What is the acceleration experienced by the arrow? Okay, that's a very similar question. So I don't think I need to draw a picture for it since it's so similar. So delta x, 0.75 meters. Initial velocity 0, final velocity 80 meters per second squared. And again, I want the acceleration. So we're just repeating the same problem, but we'll figure it out here. 2a delta x equals plus u v squared minus v naught squared. So 2 times a times 0.75 equals 80 squared minus 0. 80 squared is 6,400, and 2 times 0.75 is just 1.5. So A equals 6,400 divided by 1.5. Okay, so I don't know. Yeah?
4,266.6.
4,267. That's good. All right, that's I don't want to write on the arrow. Right. The acceleration of gravity is 10 meters per second. That's 427 Gs. That's fatal. So I don't want to do that. This is, 3.8 Gs. That's very reasonable. Roller coasters pull that kind of acceleration all the time. Most of them don't pull that kind of acceleration in a straight line. That's what makes Hulk and Rock and Roller Coaster somewhat exhilarating. Cheetah Hunt to a lesser extent too, because you're getting that acceleration in a straight line. Most roller coasters pull their Gs by turning fast. So I don't say this lightly, but kinematics problems are they're what they are. They're a lot of plug and chug once you realize what you have to do or what the information is that's given. But you can make them more complicated. Unfortunately, is once you see one of these complicated ones and see the trick, you won't be tricked again because they can only use the trick so many times. So question 7, question 8, they're very similar. They have a similar trick involved. Once you see what that trick is, you should be okay. So it says, I have a drive that is inclined in such a way that rolling objects accelerate downwards at 0.5 meters per second. This driveway has seams that are 2 meters apart. You watch a ball roll from somewhere above the first seam, and it takes 0.5 seconds to travel between seams. I think I spelled seams wrong the second time. How far above the first seam did the ball begin its roll? So it represents the first seam and the second seam, and they're 2 meters apart. Does that make sense? I start the ball somewhere above there, and the ball rolls down until it makes it to the first seam. We are told that there's an acceleration down the driveway of 0.5 meters per second squared. We're also told that the time it takes to go from one seam to the next is half a second. We want to know how far above the first seam was the ball released so that this can happen. Is that what the problem says to you guys? Everybody follow all the things we just talked about? All right. Well, let's talk about what we know. I'm going to start by writing out a set of motion variables. I know the ball traveled 2 meters between the seams. I know that that path took 0.5 seconds. And I know that during that time, it accelerated at 0.5 meters per second squared. The problem is that with that information, I could tell you something, but I can't tell you where the ball started. The part of the trip that they're asking about occurs before it makes it to the first seam. So if I look at the information I have before the ball makes it to the first seam, I want this, right? I want to know how far the ball traveled before making it to the first seam. I know it was released from rest, and I know it had an acceleration of 0.5 meters per second squared down the ramp. But that's only two pieces of information, and I can't solve the problem without a third. Can somebody make the leap of logic necessary to solve this problem? Go ahead.
We add another seam.
Don't think we can add a seam to the problem. I think the information is there that you need to solve this problem. I think you just need to see what it is. Is there anybody here who can make the leap? Go ahead. That's for it to go from one seam to the next. But we don't know how long it takes to make it to the first seam. Go ahead.
Wouldn't they all just be equally spaced, so from the top it would take 0.5 seconds to get to the first seam?
Oh, I don't think so. Because I don't know what your driveway looks like, but I have a long run of driveway before I make it to the first seam. And the first seam is where the sidewalk is. Then there's two seams, one for each side of the sidewalk. Does that sound familiar to you? Have you seen a house like that before? That's what my house looks like. So the ball starts rolling from, say, the driveway or from the garage door. It can go for a while before it makes it to the first seam. Yeah.
Do you have to solve for the starting velocity on the second one? Because it would be the ending velocity of the first one.
There it is. Excellent. You guys follow that? There's two different time intervals here. The ball starts from rest, and when it makes it here, it's got some velocity, right? That velocity is the starting velocity for the second portion of the motion, the second time interval. But it's the ending velocity for the first time interval. So if we can find out how fast it was going when it makes it to the seam, we can use that for how fast it was going from the top. Does that make sense to all of you? Let's do that. Excellent. So we're going to say that that is the initial velocity for the second portion. So I'm going to use a relationship that has everything in it except for final velocity. That'll be delta x equals 1/2 at squared plus v naught times t. And we're solving this for v naught. So delta x is 2. And I didn't stop to take into account the direction and make sure everything is been taken care of. I should have, I just forgot. So I'm just gonna make down the ramp positive, and that makes all of these things positive. Is that okay with you guys? I just forgot. So 2 equals 1/2 times 0.5 times 0.5 squared plus v naught times 0.5. We all good there? All right. You should find v naught. It's just a little exercise. Take a minute. Find v naught. Let's make sure you guys are all paying attention. So I'll pick on one of you in a second. So 3.875. Anybody else get that? Good. Arithmetic. Let's be a little bit spot on there. That becomes 3.875 here. These problems are connected together. First time interval, second time interval are connected together. You have to figure out sometimes how a problem is connected together. This problem, the rocket problem, are the same. The rocket problem's got an acceleration of the rocket at the beginning of the interval, and then when the engine shut off, gravity takes over. We have a second time interval where the acceleration of gravity is what's causing the rocket to change its speed. We use the velocity that it had after the first interval as a starting velocity for the second interval. These problems tend to be all the same. This tells you where the ball actually started. You have to pick a relationship that has these four things connected together. So I would expect that we're looking at maybe something like 2a delta x equals v squared minus v naught squared. I think that would do it. So that's 2 times 0.5 delta x equals 3.875 squared minus 0 squared. All good? 2 times 0.5 is 1, so it's whatever 3.875 squared is. So something between 9 and 16. So closer to the 16 than the 9. Yep.
15.
I don't know, whatever. I assume you have a calculator. I don't think we have to worry too much about the actual. So this is a free fall problem. Once the ball leaves your hand, gravity's acting on it the whole time. So there is a implied acceleration of 10 meters per second squared downwards. Although it's not explicitly stated in the problem, in a free fall question, they don't have to. I'm going to start by writing out my motion variables and consider what's been given to me. First thing that was given is the ball was thrown at an initial velocity of 20 meters per second. Gravity's acting with an acceleration of 10 meters per second squared. And that appears to be all that's been given, but there are clues as to what we should do next. Now you do have to make a choice here on what you want to solve for first, how long the ball's in the air or how high the ball goes. So let's assume you want to solve for how high the ball goes. There's an implied piece of information that you have to know in order to figure out how high the ball goes. And that implied piece of information is that the ball reaches its maximum height when its velocity is 0. You have to bring that to the table with you. Everybody understand where I'm coming from with that? Don't get attached to choosing up being positive, but make sure you make a choice. So again, we were deciding up is positive. That means the ball's initial velocity is positive, but the acceleration is negative. Now, I think you see a pathway to get to the answer, don't you? It's probably going to be 2a delta x equals v squared minus v naught squared. It's probably the right way to go. Now, it says be careful because your next question is to figure out what total time it spends in the air. If you use just the information given, you'd probably jump to this relationship, right? Using all that information, but now solving for time. But this would only be half the time it's in the air. Right, this would be the time it takes to get to the top. So you'd have to realize that it's going to have to come back down, so you'd have to double that time to get the whole time it's in the air. Or you could not say it stops and put a displacement of 0. This would tell you how long it takes to make it to your hand, but you'd have to use a different motion equation for that. Those are the choices that you would have presented to you. All right? I'm going to ask you to do 2 of these tomorrow.